All right, this is going to be for Chem 102. We're going to go over sections 15.3 and 15.4 in this video. So 15.3, we're talking about the entropy changes of a system. So before, when we talked about enthalpy, we talked about system versus surroundings. So let's focus on the system first. So the change in the entropy of the system is whatever the final state is minus whatever the initial state is. And so remember, we can calculate the entropy by looking at the amount of different arrangements and the Boltzmann constant. So the change in entropy is positive if we have final entropy is higher than initial entropy. Change in entropy is negative if we have a final entropy that's lower, we got worse in entropy. Alternatively, we could do some calculations, you don't need to worry about the derivation here, but we can get this formula with number of moles of a substance is equal to R times the natural log of the final volume over the initial volume. So increasing the volume can increase our entropy. So let's take this formula, take these formulas, and we're going to work a problem. So we need to think about this problem. What is the change in entropy for 1 mole of an ideal gas originally confined to 1/2 of a 5-liter container where the gas is allowed to expand to fill the entire container at constant temperature? Your R here is going to be the one with the volume in it. So 0.8206 liters times atmospheres over moles times Kelvin. Nope, sorry. R is going to be the joules because entropy is amount of energy. So 8.314 joules over moles Kelvin. Why don't you try, and here's this expanded out, I'm gonna make it a little bit bigger. Why don't you try this? There you go. All right, so if we tried it, then we would have our N is 1 mole. Our R is 8.314 joules over mole Kelvin. Our volume final was 5 liters. Our volume initial, it says it was originally confined to 1/2 of the container. So half of 5 is 2.5. We have a constant temperature, so temperature is not involved in this formula. So when we go to plug all that in, we will get 1 mole times our R, and then the natural log of 5 divided by 2.5. So you should get 5.8 joules per Kelvin because the moles cancel out. And the liters would cancel each other out because they're on top of each other in the fraction. So this is positive. Spontaneous, well, would favor spontaneity. Like this would be favorable. They didn't tell us the enthalpy change here, so we can't really tell what's going on with that. But this is saying that, yeah, that'll probably be a thing that happens. So imagine if we have a gas confined in half a container, we open up, just like this example, we have a gas confined in a container, and we open up the container, now it's got more volume, right? So it's going to be more entropy. So it's going to be spontaneous probably, assuming that we know more. There may be a reason why it wouldn't, but we don't know anything about the enthalpy, so we can't judge that. Sure. I have no idea what this slide is. They just kind of threw a weird slide in there. Okay. So standard entropy, just like we have standard enthalpy, is the absolute entropy of a substance at 1 atm. Temperature is not part of the standard state definition for entropy. So sometimes you'll be told, here's the standard entropy value. And at 25 degrees C, at 30 degrees C. It is the entropy of a substance at 1 atm. So for standard for entropy, it doesn't have a temperature as part of that standard. Because we want to think about having entropy values for different states of matter, and those states of matter don't exist at all temperatures. But we do keep it standard at 1 atm. So these are all your standard entropies, and you can imagine what we now can do with this with the chemical reaction, just like our standard enthalpies. So there are definitely some important trends to know about entropy. Liquids have higher entropies than solids. So if we look here, see the water, I believe that should be 70.0. Water is higher entropy in liquid form, or sorry, higher entropy in gas form than in liquid. We can imagine the solid would be even less. Diamond is lower entropy than graphite. Diamond is super ordered, and the more ordered you get, the less arrangements you can have to remain in that order. Look at these oxygens. They're both gases, but the more particles you have, the more different arrangements you can get. So your entropy is going to increase. So just some things to note. So liquid is usually higher entropy than solid. Gas is usually higher than liquid. The more you have of a substance, like the more atoms and stuff you have, the more molar mass you have, the more ways you have to arrange those things. So usually it increases with molar mass, it increases with molecular complexity. So the more atoms we have, the different connectivities that we have, and it increases with the mobility of a phase. So for an element with two or more allotropes, meaning carbon versus graphite. Diamond versus graphite. Diamond is not very mobile. Graphite's not either, but graphite is easier to manipulate than diamond. And so it would have higher entropy. So a molecule that has more ability to move around would have higher entropy. So for example, F2 can kind of only move the bonds in and out. So it can vibrate in and out, and it can rotate a couple ways. But look at oxygen. How many different ways can it bend? It can bend in a V shape. We can have asymmetrical stretching where we're kind of stretching each side. So we got a lot of different ways. So the more complex the molecule is, the more different ways in which that molecule can store energy. It can bend, it can move in different ways. And you can see here we have lots of different ways in which we could rotate O3 around versus fewer ways in which we could rotate F2. So O3 would have higher entropy than F2 because it's just more complex. For chemical reactions, we could do the same thing we did with the enthalpy of formation, our products minus our reactants. So we're forming our products, so we're going to be adding in the entropies of those. We're unforming our reactants, so we're going to be subtracting the entropies of our reactants. Make sure that you're multiplying by the coefficients and you're doing the sum of the reactants and products. Why don't you try this out? So I've given you the appendix 2 values for your entropies. So you have 3 different standard entropy changes. Why don't you calculate all 3 of those? All right, so hopefully you did that. We're going to do products minus reactants for these. So if you do your products minus your reactants, here are your 3 answers you should have gotten. If you didn't get that, send me a text message. Let me help you figure out where you went wrong with that. Now, sometimes we don't want to have to do math. We want to just say like, hey, what do we think the sign of delta S will be? What is the sign of our entropy change going to be? So several processes that lead to an increase in entropy are going to be melting, vaporization or sublimation, temperature increasing, and the reaction is making more particles or more gas molecules. So increasing temperature gives you more energy in general, and so you have more energy to distribute. You'll have more energy, different ways you can arrange the energy because there's just more energy. Melting is going from solid to liquid. So if you're a liquid, you have more ways to rearrange yourself. Vaporization or sublimation is making a gas. Anytime you go to make a gas from a liquid or from a solid, you're going to get higher entropy. And then if you make more molecules in your reaction, there's more different ways to arrange them, especially if you make more gas molecules. That's going to be really good. So dissolving a substance can either lead to an increase or decrease in entropy depending on the nature of the solute. So molecular solutes, as sugar, entropy is always going to be increasing. But ionic compounds, sometimes entropy could increase or decrease. It just depends on the the nature of the ions and how they work together. We'll talk a little bit more about this in class. Just know that typically dissolving is going to increase entropy, but in some cases we can see here how the entropy is lowered when we dissolve these things. And we'll talk a little bit about why that may be in class. So why don't you try to say the sign of the delta H? Is it going to be increasing entropy or decreasing entropy for these processes? Don't calculate it, just try to guess. All right, so for here are your answers. A is positive, B is positive, C is negative, D is negative, and E is positive. Let me know if you have any questions or you didn't get that, and I can help you out. And then our last section for this video is entropy changes in the universe. And so the universe is constantly increasing in entropy. So if the system is showing a positive change in entropy, the surroundings are going to be negative. So if an ice cube is melting, then the particles that used to be more free or warmer are now cooler because the ice melted and it made the thing this. So melting is endothermic. So that means the surroundings were exothermic. So they're now less energy than they used to have. So that's a negative change. A cup of hot water cools to room temperature. The system is hot water. The hot water cooling, that's bad because we're decreasing amount of our temperature, which is decreasing our entropy. But the surroundings around the hot water are increasing in their temperature. So that's a positive change. And then the entropy of the system and the surroundings are important. They're always going to be opposite. But the second law of thermodynamics say that the entropy of the universe, which is system plus surroundings, must be positive. And so there's always going to be these slight changes that can happen, but the entropy of the universe is always increasing because the universe is expanding. So we can think about the entropy of the surroundings as the enthalpy of the system divided by the temperature, and that can be a formula that we can use. So if it's exothermic, and it's negative, that's a negative and a negative, it'll be positive for the surroundings. Right, so exothermic, you're heating up the surroundings, meaning the surroundings will have a good change in entropy. So if it is a spontaneous process, the entropy change of the universe is positive. If it's non-spontaneous, the entropy of the universe would be negative for a process that's not going to happen unless we like put a bunch of energy into it. And then if you have an equal sign here, it's called an equilibrium process, which we'll talk about a little bit more later. So why don't you try this? Spontaneous process, non-spontaneous process, or equilibrium at a specified temperature. You're going to need to look at Appendix 2 in your textbook for this, or let's see if we can grab numbers. Yeah, they don't give us like a table here. So why don't you just go into the textbook, look at Appendix 2 and see if you can piece this together. So for each process, we're going to use delta H of reaction as products minus reactants to determine the delta H of the system and the delta H of surroundings with this formula. And then and this is a lot. So if you are like, hey, I didn't do this yet, but you can see how this is a problem. We can maybe do some in class, but delta H of the system is a formation of products minus reactants. And so then we get both of these things. And then we can determine the delta H of the S is spontaneous or non-spontaneous. So here's the math that they used for this. They found the delta 8, the S's, the H's, and then they calculated the system, the reaction for the entropy, entropy, enthalpy, and then they did this math. This is a lot of math for just one problem, but see if you can follow it at all. Looking at that table. Here is B. If you did work it out and you wanted to see what they got. And here is C. And then D. And then lastly, the third law of thermodynamics states that the entropy of a crystalline solid is zero at absolute zero. So if we have absolute zero, no particles are moving at all, and we have a crystal, then the entropy would be nothing, zero. No, zero possible arrangements for that because the particles aren't moving.